rather than explain, let you see the thing, then you can remember better. Right, let me just show you some YouTube. Standing wave demo.
So what we have here is a frequency generator. It's connected to
There's the vibrator there.
It's just a speaker. It's going to pump up and down at whatever frequency.
There's your frequency oscillator.
When this guy
Give you
pumps
the
up
alternating
and
current.
down, well, he sends a wave.
There's your
Sends
string.
a wave down to this end. The
There's
wave
your fixed
deflects,
end.
comes back. Now, if I set it to just any old frequency, let me.
He's changing the frequency.
Well, yeah, let's go higher.
Then you see the first
So
loop only at a certain frequency
back
only.
and forth, but these waves are out of sync, if you like. They're not exhibiting
This one is sending the wave to the right.
constructive or
The
destructive
to the left,
interference
the two wave
at one
interfere.
point.
Only
But
at a
if I
particular
set it
frequency, you see one
here,
loop.
for example,
Then two loop.
I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving.
Node is not
Here
moving
it's
at all.
up and down,
you know it's a
and
semi
here it's
point
moving
there.
up and down. And we'll see that in a second with the high-speed camera.
Okay, it's like skipping rope. This one move up and down, this one move
So
down
here
and
we
up.
have what's called the second
There is too fast to
harmonic.
see.
It's
You
the
see the
second
loop?
possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, and the middle's a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5.
Okay, so this is the first one.
And there we go.
Called the fundamental. Right? It's like skipping rope, going up and down. Right? Going up and down like that. Right? There's a fundamental frequency.
It's basically the scenario of a jump.
Or first harmonic.
Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was around 25.5.
Right, the first one is 8.5. The third one will be 3 times 8.5.
And there we go.
Okay.
So that's the
So we see 3 loops there.
How many wavelengths
1 loop,
is this?
2
Well,
loop, 3 loop.
it's 1 and a half. 1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high speed camera and verify for yourself that it is 1 and 1/2 wavelengths.
Okay, let's go back to our lecture. Okay, just now we stop there. Formation of standing wave, different mode of vibration or different pattern of vibration. Right, first one, this one loop. Right, we give you a name, call it fundamental frequency. And this 2 loop. Right, fundamental is F1, this is 2F1, and this second overtone is called the first overtone. This is the second overtone. Right, 3F1 or 3 loops. Okay, let's look at the physics involved. Standing wave in string, mode of or pattern of vibration. If the length is L, right? Remember we say the speed is determined by the tension of the string and the mass per unit length of the string. Okay, as I've given you the formula. Let's just review that in case you have forgotten. Right, that's our setup. The tension is determined by this one. And the speed is determined by this formula. This is the tension in the string. This is the mass per unit length. Okay. Right. Let's carry on deriving our equation. Remember, the length of the string is L. This is the fundamental frequency. Right? The two fixed point there, where you have the vibrator one end and the pulley at one end there. These are the nodes. Well, it cannot move. It's not cannot move. So we call it fundamental mode or fundamental frequency, one loop. Or another way of saying is first harmonic. Right? Remember, this is a wavelength. We call it lambda 1, the first wavelength, lambda 1. Right? This is half only. There's another half there. Right? So lambda half equals to L. Right? Take the 2 across there. Your L1 is 2L. Okay. Then to find the frequency is just a speed, which is a constant, divided by lambda 1. So lambda 1 is 2L, replaced with 2L. So that is your fundamental frequency, V divided by 2L. Right? Sometimes people will use, instead of frequency, we use nu. This is a Greek alphabet instead of F. It's the same thing, just a matter of choice, that's all. It looks like V, that's all. Okay, so that's the fundamental frequency. You have to remember that. Or derive it. If you don't want to memorize it, derive it. Right? Speed divided by 2L. Okay. So remember that from peak to peak is a wavelength. We are looking only this side, that's all. That's half is a wavelength. Right? Between 0 to maximum and back to here is half a wavelength. Okay, second mode, 2 loops, 1, 2. Right? That's what we have derived for the first mode of fundamental frequency. Length is the same, we haven't changed the length. You have the node there, center there, one node, then there's one node there. Right? The fixed there is always at the node. Center now becomes the node. Right? We call it the first overtone. Right? This is only more for music lover lah. They should know all these things, but ours we are not so much interested in that. We know the second is 2 loop or second harmonic, first overtone. So it's a different wavelength. So we give it lambda 2 equals to length L. Right? Let me just adjust it slightly. Okay. Right? So this is a different wavelength from the previous one. We call it lambda 2. Right? Lambda 2 equals to L. Or remember that previously, your L is half lambda 1. Okay, we can express it in terms of lambda 1. Okay, lambda 2 is L, so L is half lambda 1. Can either write in terms of lambda 1. So F2 is V over lambda 2. So lambda 2 is L, put the L there. Okay, V over L. Then V over L, remember V over L is F1. So it's f1 over 2. So it's 2f1. Okay, take this across there. 2f1 is v over L. That's what we get. Can either express a new wavelength, lambda 2, in terms of the old wavelength, lambda 1, right? Or we can express the frequency f2 respect to f1. How is related to f1, right? So this is twice the frequency. Okay, second overtone, this is the one. This is third loop, 3 loops, second overtone or third harmonic. Right? This is a different wavelength, so we call lambda 3. This is one wavelength, this is another half. So it's 3 over 2 lambda 3 equals to L. Okay, we can take our, we want to find lambda 3, we take our 2 across there, lambda the 3 down there, we get this one. Or to express it in terms of lambda 1, right? Lambda 1 is 2L, so this 2L is lambda 1. Okay. Right? In terms of frequency, F3 is the speed. Right? Speed is always constant, divided by lambda 3. V lambda 3. Right? Lambda 3 is 2/3. Right? 2L over 3. 2L over 3 times 3 times 3, we get our 2V over 2L. Sorry, 3V over 2L. Right? And then from here, V over 2L. V over 2L. This V over 2L is F1. So it's 3F1. Right? Let's just summarize for what we have done. A general equation. Right? For higher one, instead of going to draw all that, we can have a general equation. In general, the nth frequency equals to n times f1. N is a whole number, 1, 2, 3. So the fundamental frequency is V divided by lambda 1. Then in terms of lambda m is lambda 1 over n. Right? This one is multiplied by frequency, fundamental frequency times n. This fundamental wavelength divided by n. Right? N is still the same, whole number. Right? Lambda 1 is 2L. Remember that? You have derived all that, refer to your note. Or we can summarize in this diagram. Same thing. Right? See all together there. We have derived for you earlier. You can refer to that. Okay. Let's now look at more information. Second harmonic. Let's just refer to our first overtone. All points between the successive notes are oscillating in phase. This is the note. This is another note. So these are successive notes. So all the points here or particles there are same phase. They are all down there. Now they are going to move up. Or between these two successive nodes, all the points here are moving up. All together moving up. That's why we are saying they are in phase, then moving down. Point to the left of a node is 180 degrees out of phase. It points to the right. If we take a node here, right to the left here, this point, and that point there, they are 180 degrees out of phase. They are not the same phase. This one is moving down. This one is moving up. Okay, all of them. All this part is moving down. All this part is moving up. Okay, or if you look at this one, all the points here is moving up. All these points are moving down. Okay, so of course you want to compare the difference between progressive wave and standing wave. Page 61. Right, there's your standing wave. We can look at DAP, right? Displacement. At nodes, the displacement is permanently 0. Right? At nodes there, it's not moving at all. It's at rest. Amplitude. Each point along the wave has different amplitude of vibration from neighboring point. Right? Between the node there, each point there got different amplitude. Largest one will be at the node. Same here. Right? Between the two nodes there, each point has got different amplitude. The largest is at the node there. phase at point between successive nodes. Successive node is either these two or these two. These two are successive node or between this one and that one there. The points between successive nodes, the vibration are in phase. Right? So all these are moving down. All these are moving up. That's why we say they are all these are in phase. This is successive node. This successive node. Right? So all these points are moving down. All these points are moving up. Energy. The energy stays at the same position along the medium. The energy doesn't move. It's just here only. So the fundamental mode is just within there, vibrating out and now the energy is there. Doesn't move along. Right? It's just here. How about progressive wave? Right? It's moving. Right? Displacement, no points at zero displacement permanently. You cannot see that. Every point will vibrate. And you will have a displacement at some other time. Maybe zero at one time. Then after that, you will have different displacement. Amplitude, every point vibrates with the same amplitude. That means every point, right? They may have different amplitude at a particular time, but after a certain time, they will reach a maximum amplitude. Phase, the phase of neighboring point, right, are different. They are all a different phase. Whereas neighboring point between two nodes, they are moving in phase. Energy, the wave energy move along at the speed, right? Whereas for energy, the progressive wave carry along the wave. So that's why you see a cork, right, in the river or in the pond there will be vibrating as the ripple move past it. The progressive wave carry energy. We can compare the two if you like. Right? Can compare the two. Okay, we can use the rocket DAP. Have you remember DAPE? Have you remember displacement, amplitude, phase, energy? You have to memorize this one. Okay, let's look at the maths. Right, these are the maths you need to know. Right, these two. Right, we look at this one. Now we look at the mathematics, how standing wave is formed. Previously, we looked at the experiment. Right? That's one way. Y1, given by that equation. This one is traveling in the negative x direction, whether it's positive, it's traveling to the left. Right? Negative means it's traveling to the right. That's what we say. One wave traveling to the left, one wave traveling to the right. The two must have the same frequency, same amplitude. And we add them up. Right? We add them up. Right? The x here is just this one. The y here is this one. Okay. Okay. The x here is here. This is the y. So the first one, you just add them up. Add these two up. So this one goes off. This one is 2Wt divided by 2, it becomes Wt. Right? The next one becomes minus because you add, it becomes minus. So you minus this one, minus this one. This one goes off. Minus becomes plus. So it's 2kt. Okay, divide by 2. Right? Divide by 2. Can? Any question? Srini, are you sleeping? Okay, now it's your turn to do for me this maths. Right? That is give you the equation. This is in terms of sine, are you cos? These are your two waveform. Find for me the resultant waveform. Tell me the answer. Okay, work it out. Use paper. Make sure you bring your paper every time for class. What's the answer? Yeah, just use this equation. Already given you the equation. Okay, Ken, what's the answer? Yeah, what's the answer? Ken, just the math only. You should know how to derive the two equation. Just now I was using sine, this one is using cos. Right? Just this is your x, this is your y. So what's the answer?
Two.
Okay, what's the answer?
Two.
What two? What do you mean two? What's the answer? You're not doing at all. What are you happening? If there is an answer. Right? Add them up. You get 2a cos omega t cos kx. Yeah, that's your cos. That's your 2 there. That's your a. Right? Cos. Where your x is now your same thing. Your y is now there. Y on this equation. Compare. Right? Compared to the previous equation, we can see that if you use cos, the omega t is the one that's changing. Right? This become cos. This becomes sine. Just now you use sine, but this two is still the same. Right? Cos kx is still the same. Okay, let's look at amplitude, page 60. Right? There's the equation that we have derived. Supposing that both of them are sine. Right? This is the amplitude. 2a cos kx. Right? This is sine omega t. This is the changing with time. Right? We see that it depends on the horizontal distance. Remember, this is your cos graph. This is your 2a. Right? This graph. This graph there. Depends on horizontal distance. It depends where you are. The amplitude. Right? The amplitude there. When it is 0, right? 0. Amplitude is 0 here. And 0 here. Okay. So it becomes your 90. Right? 3 pi over 2 or 5 pi over 2. Right? This is 0. It's pi over 2. Right? So 0 is pi over 2. This is pi. This is 3 pi over 2. Right? 0 at this 2 point there. And then the other one, you just add pi, that's all. So x. Right? X. Right? Cross multiply. Take the lambda up. Take the 2 pi down. Right? Pi and pi will cancel off. This is lambda over 4. Right? Same as this one. Take lambda up. That's your lambda. There's your 2 pi. The pi and pi cancel. 2 times 2 is 4. And then there's your 3 there. And so on. Right? Between n and n. Right? We previously say is lambda over 2. Right? N and n. These two subtract. Lambda over 2. Okay. Remember your WT. Omega t equals to 2 pi over t. So when you put your t equals to 0, your sine omega t equals 0. Right? At 0 time, this is 0. So everything is 0. Right? At a quarter of the period, right? Quarter of period, then you put this one, t is t over 4. This one becomes your pi 90. Pi 90 is 1. Right? This becomes 1 sine omega t. So we get this equation. This is a quarter of the period later. This is a waveform quarter of period later. Right? Its maximum, you can put 2a. That will be 2a. That minus 2a. to 8 cancel, it becomes 1. Right? So 1 is at 0. At 0, pi. Right? This is your 3. This is your 2 pi. Okay, is 0, pi is 2 pi. Okay. Right? In terms of x, that's your antinode. Right? In terms of x, there's a lambda. Right? X is b0. The second one will take the lambda up. Pi and pi cancel, divided by 2. So lambda over 2. This one 2 pi and 2 pi cancel, take the lambda up. So you got lambda. Right? So there's an antinode at 0. Right? This is half lambda. This is your lambda. Okay. So A to A, this one is half lambda, or this one, the difference between this one is half lambda. From a node to an antinode, right? You just an, okay, half lambda minus quarter, right? Because a quarter lambda, right? This is using maths. Previously, we just show you the picture, then you can identify it easier. Okay, I think we have completed already. Anything else you want to ask?
No, sir.
We have completed already, so I expect you to don't have much time to do any example. Tomorrow we'll spend time doing example. Right? We have completed checkpoint 2.3, 20.3, 20.4. So tomorrow I think I will spend time doing the solving problem for you. 20.2, 20.1, 20.3, 20.4. We've got time, we try to finish 20.5. So I expect you to do your homework tonight. Anything else you want to ask? If not, I will stop here today.
No, sir.
Yep. Anything else you want to ask?
No, sir.
Okay. If not, I will see you tomorrow, 9 o'clock.
Okay. Thank you, sir.
Bye-bye.
Bye-bye.
Right. Make sure you review through before you come for class tomorrow. If not, you'll forget everything.
Okay, thank you, sir.
Bye-bye.
Bye.